Today is May 8th, 2007. Our guest for an oral history interview today is Roger Chassay. Roger, it's good to have you here. I'm Charles Lundquist. These oral histories go into the archives at the University of Alabama in Huntsville and also go online very quickly after the interview. Roger, we like to let people start out by telling a little bit about their youth, where they spent their youth, where they went to school, and how they got into the space program. Can you do that, please?
Okay. Well, I was born in Chicago, Illinois in 1938 and lived there until I started school. We moved south and I went to elementary school in Columbia, Mississippi. And then we moved to Louisiana, and I spent the rest of my schooling there in Louisiana and graduated from Louisiana State University in 1961. Went into the Air Force for 3 years, and NASA offered me a job. And I had always had a strong interest in science and mathematics and engineering, and so I gladly accepted and became a part of the space program.
What year was that?
That was 1964, and my first job was at Michoud Assembly Facility in New Orleans.
Oh, tell us about what you did there.
Well, I was, as NASA often did, is they would make you an instant whatever, and I was an instant reliability engineer. So I had to learn about reliability engineering and mathematical models and predictions on success for the Saturn 1B rocket at that time. That was the junior rocket to the moon rocket.
Well, how long were you at Michoud?
I stayed there about 2.5 years and got an offer for a promotion to come to Huntsville and working in the same area in the Saturn 1B program office, in the booster stage office there, and spent about 3 years there before I moved on to the Skylab program.
Well, who was your boss in the Saturn office?
Art Thompson was the booster stage, S1B stage project manager, and he came out of the old research projects lab. Perhaps you knew him.
Yes, I knew him well.
And I worked for him for, I think, about 3 years.
And then moved on to
Skylab, and at that time it was called Apollo Applications. Very interesting. The term Apollo Applications seemed to attract no priorities, no money, no large numbers of people, no emphasis. And one day we were working very, very, very hard. One day we got a notice that they were changing the name of Apollo Applications to a name called Skylab. And I remember being very irritated. I was going to have to change all of my files because of this new name, and I thought that was just ridiculous that they would change the name of a program in midstream. But all of a sudden, the term Skylab became an everyday word. People on the street understood it, Congress understood it, and certainly the leaders in NASA understood it, and we began to get priorities. We began to get good people. We began to get funding. And we ended up building the world's first large space station.
Well, that's an interesting lesson in how to deal with the public, isn't it?
Yes.
Now, what was your role at Skylab? What did you work on?
I was, the heart of Skylab was something called the instrument unit, where all the electronics were housed, and the airlock module had a peculiar name because that happens to be where the astronauts would ingress and egress from the Skylab space station. But it also, much more importantly, housed all the controls for the entire Skylab. My job was to review. I headed up a team that reviewed all of the individual components that we had gotten from the Gemini program. And Gemini was a 2-week, these components had been designed for 2 weeks in space, and we were going to use them for some 10 months in space. So it was my job to run the acceptability reviews to see if we could extend the life of these 2-week items to 10 months.
Where were you when the launch accident took place or anomaly took place?
I was down at Kennedy Space Center. We had 4 people from the airlock module and multiple docking adapter. I was also in that area. We had 4 people from NASA Marshall down at Kennedy Space Center at that time for the pre-launch operations, which took about 9 or 10 months, and we stayed there.
You were down there that long then?
Yes, we moved the family down, and I think we had probably on the order of 100 or more Marshall people down at Kennedy Space Center. The largest component were in support of the Apollo telescope mount, but a few of us were supporting other parts of the Skylab, and so we were still down there at the time of the launch and the disaster that occurred shortly after launch or during launch.
Were you involved in the fix for it, or?
I was not. We were all in a state of shock there, and we were all available 18, 20 hours a day to render whatever support we could. But other than listening into the emergency telecons and participating in a few activities to collect data, I didn't have any particular role in the solution.
But your controls worked.
Our controls worked beautifully.
That was important. Of course, in the recovery.
Right, and we were. I was also a part of the mission control team for about 9 or 10 months here in the Huntsville Operations Support Center, and the first few weeks were just very harrowing there, where we were teetering on the brink of overheating the Skylab in order to get electrical power, and if we got too much heat and reduced the heat in the Skylab, then we weren't getting adequate power to keep the systems going. So it looked as though there was no mutually beneficial way to run the Skylabs in the first few weeks.
But you found a middle ground eventually.
Well, of course, I didn't find it, but
the middle ground was found.
Right. J.R. Thompson, as you probably know, headed up a team to try to discover a way to reduce the heating of the Skylab and still have the Skylab pointed, solar arrays pointed such that the electrical power system could get enough power to run the entire system, and that was successful.
Well, as Skylab went through its 3 phases, how did your involvement evolve?
Well, I was fairly young at the time, and I was very honored to be selected as what was called the Operations Support Manager. And the Operations Support Manager ran each daily shift of technical teams supporting Skylab from the Huntsville Operations Support Center. So I was a very young, or I thought I was young, supervisor at that time, supervising the technical teams from Marshall supporting the mission. So I would chair each one of the meetings to begin an 8-hour shift to determine what the emphasis for that shift would be, whether it was experiments, whether it was troubleshooting thermal systems, troubleshooting data systems, troubleshooting the electrical power system. So the Operations Support Manager was a very fun role, and I did that for the entire mission, 9 months or so, and we rotated shifts, and for the first time in my life I had a regular shift at times from midnight to 8 a.m., the so-called graveyard shift, and I thought that was very difficult.
Well, a lot of the planning got done during that shift, though.
A lot of the planning was done on the graveyard shift, as you know, and that was what the astronauts then would execute that plan during the day period, while we would do the planning at night. But we would rotate out, so I had plenty of day shift and evening shifts as well.
Well, when Skylab was over, what did you do next?
Well, that was probably the most exciting part of my career, at least at that time, was I was asked to head up a small project to launch sounding rockets out of White Sands Missile Range. And was told generally what was intended there. The space shuttle was not flying. The first flight had been delayed many times, I guess, due to difficulties with engine development. So in the meantime, we wanted to begin to do materials experiments in weightlessness for short periods. And the sounding rockets out of White Sands could give us on the order of 4 to 5 minutes of weightlessness. And so I was able to even name the project. Not many people in NASA get to name their own project, but I named it Space Processing Applications Rocket Spire. And I took a leaf from the page of Skylab. I wanted a catchy name that people could identify with, and certainly.
So you learned a good lesson.
I learned a good lesson from Skylab on a much smaller scale. This was not a very large project, but I was able to get congressional attention to SPAR and NASA headquarters attention to SPAR, and the leadership here at the Marshall Space Flight Center to SPAR. And everyone seemed to like the little project, and we got quite a bit of attention, particularly since we were the only flight project at the Marshall Space Flight Center at the time because of the delays in the beginning of the flights of the space shuttle.
What kind of things did you do with Spire? Can you describe some of these experiments?
Well, I met this gentleman from the Space Sciences Lab by the name of Dr. Charles Lundquist, and he had a team of scientists, PhDs, who were specialists in physics and chemistry and other disciplines, and they had successfully proposed a number of experiments to be done in space to determine how materials behaved in weightlessness. And these were fascinating experiments, a wide variety of those, from fluid dynamics to metal processing to optical systems, and each one of these, over a period of 4 or 5 years, I guess, led to more sophisticated experiments on the space shuttle when it began to fly.
How many rocket launches did you do?
We had 10, and it was very, very exciting work, very difficult work. It was one of those things where you learn a lot of things. I learned that, to my amazement, even though we had a lot of dedicated scientists and a lot of dedicated engineers, they didn't particularly respect each other. And so even though we both studied the same laws of physics, somehow the engineering disciplines were such that they liked their methods of employing their technical disciplines in a way that the scientists didn't care for. And so one of my main jobs was to make the two camps work well together, and we did.
So the Spire program continued until the shuttle started flying, or did it continue after the shuttle flights got going?
It actually was discontinued, but yet continued in Europe. The Europeans did not have good access to the space shuttle early on, and they had encouraged NASA to work with them to help them develop their sounding rocket program. So I made a few trips to Europe to pass on a lot of our lessons learned to the European Space Agency, in particular the German Space Agency, who was their arm for doing sounding rockets. And so oddly enough, the Spire program became the Texas program, TEXUS, and I don't recall what that acronym stood for, but it was some German equivalent to Spire. And they flew sounding rockets out of Sweden for many years, and for all I know are still flying.
Well, when you finished the Spire project, what did you move on to?
Well, the Spire was the first flight arm of the Space Process and Applications program to study materials behavior and weightlessness, so that those new processing techniques that were found in weightlessness could be used in manufacturing techniques to develop new materials on the ground. And so I worked in the so-called Space Process and Applications Program, or Materials Processing in Space. It had both of those names over the years. I worked in that program for some 20 years, including the early years of Spire. And in particular, I was a project manager for some dozen or more materials science projects where we were doing experiments in space, and the one I liked the best was protein crystal growth, where a lot of the people from the University of Alabama, Birmingham had specialized in protein crystal growth and weightlessness, and so I was happy to be the project manager, among other things, of the protein crystal growth experiments, the early ones.
Can you tell us a little bit about the motivation for that? I'm sure you had to deal with that.
That was delightful. There's Dr. Charles Bugg from the University of Alabama, Birmingham. Perhaps you know him.
Oh, I know him well.
And he was what I call the Vince Lombardi of the material science community. He knew how to inspire people. He had a great vision for the long term. He could work with a common person in the laboratory, very, very bright. He could work with the politicians, and he could organize a team and push that team to heights beyond what they individually thought they could accomplish. And the general concept there is that protein crystals are extremely delicate, and they're also extremely complex. The molecular weight of a typical protein is around 100,000 or so, so it's like if you look at the molecular structure, it's like looking at a pot of spaghetti. There's just many, many arms to the individual protein. And it's very important to know where the active sites are within that protein, and it was very difficult to determine the molecular structure on Earth, because as you tried to crystallize these proteins, then they would tend to collapse and agglomerate and clump together. And so the molecular structure was extremely difficult to determine. But if we took those same delicate proteins into space and let them solidify in a very passive environment there of space, the lack of gravity and the convection caused by the gravity, then we were able to get just beautiful crystals, and then preserve those crystals and bring those back to Earth, and then bombard them with soft X-rays to determine the molecular structure.
Yeah, that's the key. In order to get the molecular structure by standard X-ray techniques, you had to have a very fine crystal, a very pure crystal, and those could be grown in space, but not easily on the ground.
Right, and we could get much larger crystals in space as well by having a lack of convection, the lack of movement of the fluids in the experiment, and we had up to, I think, 50 or more, perhaps even as many as 100 candidates. The human body has something over 10,000 different proteins in it, and each protein has a different function. And most of the diseases of mankind are misbehaving proteins. So the idea was to find what the molecular structure was for those misbehaving proteins, and then design a drug that would go into the active site of that protein and block that misbehaving protein from doing its damage to the body. And the theory is still brilliant. It's a great idea, and I think over the next 10 to 15 years we'll be seeing many more designer drugs that would be such that they could block these misbehaving proteins, and yet with a lock and key kind of design, not have these bad side effects of many of the drugs today that do a good job perhaps, but also render the patient in a state that's not very desirable because of the serious side effects.
So you were involved then in a large number of shuttle flights that carried these experiments?
Yes, I had payloads in the middeck of the shuttle, out in orbit or bay. We carried a large 2,000-pound payload that that I was fortunate to be the project manager of, called the Materials Experiment Assembly. And we flew that out in Orbiter Bay on the back of a space lab and actually controlled the mission out of Germany. So I was in Germany for the mission control. There was the first time a shuttle space science mission had been controlled outside of the United States in the middeck of the orbiter. Then we did the protein crystal growth experiments and other small experiments that could be done in middeck lockers, the crew lockers that were surplus available to us to put experiments in. And then I was also the project manager of the fluid experiment system and the vapor crystal growth system that flew inside the Space Lab on Space Lab 3. And I took that project over 9 months before the launch, so they called me an instant expert. It was a very, very complex set of experiments. And the mission was over before I really fully understood the equipment, but my job was to lead the team, and we were successful in doing that.
Well, your career progressed, I'm sure, after that. How did it evolve?
Well, let's see. After Space Lab 3, then I moved further up into the management of the Space Processing Program, and I was the deputy manager of our project office. We had a substantial amount of income at that time coming from NASA headquarters and originally from the appropriated in Congress, of course.
Who was the manager at that time?
James Brett at NASA headquarters, and at Marshall we had a variety of managers. I guess the first one was Colonel Brian Montgomery, and then as he left, Eugene McCannon from Marshall's Materials and Processing Lab took over, and then for a while we had Harvey Herring, who had originally been at Langley and then at NASA headquarters. He took over the program, and then John Price ran the program for a while during the period where I was the deputy program manager.
Well, after that, what did you do?
Well, about that time the space station was beginning to get quite a bit of attention, and it had a very, very rocky start and had major redesigns seemingly every 9 months or so, and so I was the liaison between the Materials Processing and Space Program, or the Space Processing Applications Program, and Space Station. And so I chaired the two of the committees. One in particular was the Space Station Requirements Integration Group, I believe it was called, for the utilization of space station by materials processing. And in fact, that was the original driving requirement for the space station, was to be able to process materials on a large scale in Earth orbit. So I chaired that NASA-wide committee for about 3 years, I guess, and
that involved the vibration specifications for the station, did it not?
Yes, that was very interesting.
That's what I'd like to let you talk about that.
Well, you had an individual working for you, a very energetic, brilliant fellow by the name of Dr. Robert Nieman. Bob Nieman was, I think, named as the program scientist for the space station, and so he jumped into that job with his typical energy and inquisitiveness, and he found that the space station was very poorly designed or poorly laid out for materials processing because of the dynamics, and they had put the laboratory modules in the outer perimeter of the space station, which provides the worst possible microgravity environment. And so through Bob Nieman's involvement, we were able to get the entire concept for the space station changed to where the materials processing experiments would be done near the center of gravity of the space station instead of near its outer boundaries. And so it was really quite exciting, and to be able to see that happen, to see one man and the people supporting him be able to change the concept that drastically, even though there were many engineers who thought otherwise, thought that we ought to leave the space station as it was.
Well, eventually space station got launched. Were you still on board then?
I was beginning to move on to other things. We had reorganized our program office several times, and NASA Marshall had also gotten interested in environmental science, and we had people for many years studying such things as lightning and changes in the Earth environment and that kind of thing. And Marshall formed a global hydrology center, and I was asked to join the Global Hydrology Center and be the, this is another instant expert kind of a job. I was to provide the supercomputers for these scientists that were studying these global environmental models, and so I was supposed to be the instant expert on, and the project manager to get supercomputers for this global hydrology group. Fortunately, I didn't have to do that very long because I didn't understand such things as megaflops and those kinds of things, and also didn't understand how anyone could need computers that were much larger and much faster than anything the world could build. So I moved on, but stayed in that group, but I became the project manager for the world's first 2 lightning detection satellites. The LIS, the lightning imaging sensor, and its predecessor, the OTD, the optical transient detector. Turns out people in the global hydrology group had realized that you could observe and study lightning much better from Earth orbit than you could from the ground, and we were able to detect perhaps 3 times as many lightning strikes from Earth orbit, and then determine what that meant in the way of storm intensity and the likelihood of tornadoes and that kind of thing. So I ran those 2 flight projects, and still own, I guess, those 2 pieces of orbiting equipment that detect lightning from space.
Get involved in any of the studies and the emerging understanding of upward lightning, sprites and all those things?
Yes, those were the flower children of the science group. There were as you know, Skeet Vaughn, I think, was probably the earliest pioneer in that area, and yet Skeet had a habit of not publishing his work, and in his day-to-day methods, he preferred more empirical techniques, and so he had early on that those concepts didn't get much technical respect, and but as I understand it, eventually people came to respect that science, and I've kind of lost track of where it's gone, but I believe that's a legitimate part of studying.
Oh yes, and it's a very hot topic in trying to understand the electrical circuitry of the Earth, so to speak. That was an interesting sideline that came up during that period.
I thought it was fascinating. Skeet never seemed to get much respect in the science community, and yet he was able to, through his own powers of persuasion, buddy up to the astronauts and have them do quite a bit of science for him that laid the groundwork for these later studies.
Well, later some ground-based observers who were observing normal lightning with high sensitivity devices started seeing all this upward discharge from thunderstorms, and soon had a good database on it and became very well accepted. Now the lightning satellites, of course, still can continue to be important. If you watch the weather, certain weather channels, you see pictures of representations of where lightning strikes are happening. Good way to track thunderstorms.
We were quite frustrated during that period, even though we were successful in getting our, at least my aspect of things done, by getting the 2 satellites finished through research and development, get them through the pre-launch operations, get them functioning in flight, and acquiring quite a bit of data. At the same time, we were working for follow-on proposals where we wanted to put geostationary satellites over the United States, over the Pacific Rim nations, over Europe. And we actually did a study that showed that we could, for a relatively small investment of about $35 million, we could easily recover that money in avoidance of losses within just 6 months by having advance warning on severe storms and advance warning on perhaps tornadic activity. And it took a long time to sell that concept. They're still making progress on it, but for me as a engineer and a manager, it seemed like it was a great investment. Invest $35 million and recover that in 6 months, and yet it's taken the program perhaps close to 10 years to almost sell that concept.
Well, when you finished the lightning satellites and instruments, what did you do?
Well, since we didn't get the follow-on at that time for the applications of this lightning detection, and that's the geostationary satellites over the United States, then I went to see a good friend of mine, Rex Jevedon, and asked him if he needed any help. And he and I were delighted to be able to collaborate together on the Gravity Probe B, the so-called Einstein experiment that Stanford had originated some 30 or 40 years earlier. And so I became the assistant program manager under Rex Jevedon for the Gravity Probe B program.
There you interfaced with some very interesting people, I know.
Very fascinating. There's a Professor Francis Everett out at Stanford University who's a world-renowned scientist and yet just genuinely a nice person. And he had been with the program for a long time, and he and I became friends, and we worked along with his team and our team here and others. We worked very intensely for about 5 years, and that resulted in a highly successful launch in the year, I guess, 2004, and we're now looking forward to hearing the results of that sometime later on at the end of this year.
Well, after Gravity Probe B got launched, what did you do?
Well, I stayed with the team for a while. The operations team was pretty much run by the scientists, but there was some need for support, and I worked in the public affairs part of that, where we were writing daily reports on the progress each day, and also trying to put a long-term spin on what this really meant. The fact that Einstein in 1916 had predicted the warpage of space and time due to the presence of a massive object, and also warpage in space and time of the spinning of a massive object. And here he had that theory in 1916, and no one had ever been able to test that theory. So it was quite exciting. And with Einstein being the man of the Time magazine man of the century, I guess, in the year 2000, there was a lot of public interest in the experiment. Our main difficulty with the experiment was that the Earth is actually quite tiny on a galactic scale. And so when you run this experiment to study the warpage of space and time in the vicinity of the Earth, since the Earth is quite small, then the warpage of space and time is almost infinitesimal. So that's what the experiment was trying to do, is measure this quite extremely small warpage of space and time. Would have been much preferable to run it near a brown dwarf or a black hole, where the warpage of space and time would be extremely significant.
A little harder to get to, though.
Harder to get to, so we couldn't figure out a way to get our instruments to a brown dwarf or a black hole, and so we did it in the vicinity of the Earth. and that made the job extremely difficult. We had over 40 boxes of electronics half the size of this table, just crammed full of multi-layered printed circuit boards. All of those large boxes worked beautifully throughout the entire mission, much to my surprise, because we had a lot of difficulty in manufacturing them. But once they got manufactured and tested, then they worked just beautifully through the mission.
I gather there was some problem with the drag compensation system.
Well, there were. It was called the program was, and the satellite was called the program of 7 zeros, and one of the zeros had to be zero drag, and so it was a mission where the satellite had to have the same velocity for an entire year's period, and that meant that any drag that occurred to the space vehicle had to be compensated for by an equal and opposite thrust. And this thrust had to be quite small, but it had to be consistent throughout the entire year. And so the people at Stanford, working with their support contractor, Lockheed, had come up with a device to give that offsetting thrust for the drag component, and to my knowledge, it worked rather well.
I believe there were times when it didn't, or the sensor didn't give it the right input.
Okay, well, you may be more knowledgeable than I, but the overall design of the system and the testing of the system seemed to work. The concept seemed to be satisfactory, and then from the more recent reports I've heard of the overall mission success, it seems as though whatever difficulties they had, maybe they overcame those.
Well, there were, I understand, some periods that were not drag-free, so that's part of the problem of doing the data analysis. You have to patch together the drag-free periods with the non-drag-free periods.
Right. A fascinating mission, though. Can you imagine pointing a large spacecraft, 7,500 pound spacecraft in Earth orbit, pointing it at a light source that's 300 light years away? In other words, when we launched in 2004, the light we were pointing at had been emitted from this star around the year 1704, and we were pointing at this very it's actually not a very bright star magnitude of 3 or 4, I believe, and brightness magnitude, and to be able to hold that precision pointing on that star for over a year was just a magnificent accomplishment.
And to correct for the motion of the star, since it had a proper motion.
Right. As an engineer, I'd never heard of proper motion, but turns out the proper motion this is actually a binary star, and then as we neared launch, we found out there's a tertiary star in that field of view. So you had two stars there overlapping each other in our field of view, with a little tertiary star also cluttering the image. And then each one of those stars had various apparent motions that had to be studied, and there's about 6 different components of those spiral motions or wobble motions, and our job was to find the centroid of those 3 tiny clusters and be able to point at the centroid of these stars where the light had been emitted in the year 1704.
Very challenging.
Very challenging. The proper motion was a big job.
Well, we have to wait another few months to hear the final results from that.
Right. Well, the data is all embargoed, and there's two science teams checking each other's work, and all this takes quite a bit of time, and so I'm no longer a part of the team. I'm not a part of the science team, but just judging as a manager and supervisor, they seem to be an optimistic group and cheerful, so I read from that they're going to give us some excellent results.
Very good. Well, where did your career take you next?
Well, I had spent, I guess, about almost 42 years working for the government, 3 years with the Air Force and 38 plus years with NASA, and so I decided to retire, and I actually worked as a contractor for NASA Marshall Space Flight Center.
What year did you retire?
I retired in the year 2002, and I still continue to work on the Gravity Probe B as a support contractor for about 2.5 years, and then I'm now almost fully retired. I work less than or fewer than 2 hours a week.
Well, as we near conclusion here, are there any general observations you'd like to make for the record or for the benefit of the young folks that are now coming on board and starting to do the things that you've done? A chance to pass on some of your philosophy.
Well, I don't know that it's worth that much, but I think one of the things I found over my career was that people who were only interested in the pure science or the pure engineering of what they wanted to do, or that what NASA wanted them to do, then at times they were very frustrated, because there were times where there was no science to do, there was no engineering to do. There was just fighting through either bureaucratic problems or fighting through organizational problems, or just getting adequate laboratory space, or getting staffing properly set up. And so there were periods where you just had to fight through that and be patient in order to get to the true nuggets of what we were about. And I think the people that were most successful in their careers were ones that could tolerate those periods and get on to the exciting things that we did. So for a young person embarking on a career in this area, I'd just say you have to tough it out sometimes, but it's a very rewarding thing. I've always told my close friends from back in high school and college that I go back to visit in Louisiana that it's just been a delightful experience to be able to do something no one has ever done before, and instead of building houses or building dams or building things that people have done again and again, working with NASA, we were always doing things that no one had ever done.
So you feel you had a fun career?
Oh, it was delightful. I'm ready to start again.
Well, maybe that's a good place to end. We surely thank you for coming in, unless you have something more you want to add for the record.
It's been my pleasure being here.
Thank you very much.
Thank you, Chuck.